This video goes over a practice circuit so we can apply all the concepts that we learned on previous videos. And it's going to be a little bit longer video than the previous ones, so just hang in there. And as we go through this exercise, you can stop and try to do it by yourself and then validate with the answers that I will keep providing. The circuit that we're going to be using is this one, and I'm going to follow a set of steps to get the answer of this circuit. And the steps that are going to be highlighted in green are going to be done in the time domain, and if they are in purple means that I'm in the Laplace domain. We're going to start by finding the initial conditions, then going to this S-domain model, extract the algebraic equation, check if that equation is correct or wrong, and if it's correct, then we do the partial fraction expansion, which prepares our equation to take the inverse Laplace, and at last we plot and validate our answers. Alright, so let's go and find these initial conditions. Initial conditions means that I'm trying to find answers for t less than 0, means that everything is steady, DC, and the capacitor is going to be an open circuit. And if you struggle understanding why the capacitor is an open circuit in DC, recall the equation for the current that flows through the capacitor, which is equal to C times the derivative of the voltage across the capacitor. In DC, that derivative is 0, which gives you a current equal to 0. That means that our capacitor is an open circuit. The inductor, on the other hand, is going to be a short circuit because the equation tells us that the voltage across the inductor is L times the derivative of the current over time. Well, again, DC, the derivatives are 0. That means the voltage drop across the inductor that it's 0. So this potential is the same as that potential, and I get a short circuit. The initial condition for the inductor is pretty straightforward. Open circuit, no current flows through the inductor, so 0 amps. And for the capacitor, we can rewrite the circuit or redraw the circuit, and we see that the voltage across the capacitor is the same as the voltage across the 2 ohm resistor. If I apply the voltage divider on this circuit, I get a voltage of 5 volts across the capacitor. Alright, now we are in good shape to start moving to the Laplace domain. We have our initial conditions that are important for the Laplace model, and there are two ways of drawing these design in the Laplace domain. One is to use our initial conditions as current sources, and in this case I only have one, which is related with our capacitor. The inductor, it's 0, and I'm representing the initial voltage as this current source. And another way of designing this circuit is to represent that initial condition as a voltage source. Alright, so both are going to work. You're going to pick the one that makes your life easier to extract the parameters that you want to extract, but you should be able to get exactly the same result whatever model you use from this domain. Alright, so now let's go over extracting the algebraic equation out of the circuit. I'm going to use the current source model. You can stop the video and use, for example, the voltage source and see if you can get the same answer. You should get the same answer. And I'm going to focus on trying to extract the equation in terms of the current that flows through the inductor, so this IL of S. And the first step that I'm going to use is KCL on this node. There are different ways of approaching these. Again, you can, for example, now we can treat this as a linear circuit. We can, or as a resistive circuit. I can put these two impedances in parallel together and then apply a source transformation on that, and then I have a circuit with all elements in series and apply KVL. But I'm going to use KCL. KCL tells me that the nodes coming in are equal to the KCL tells me that the currents coming in are equal to the currents going out. So going in, I have the current through the resistor plus the current through the capacitor equals to that initial voltage represented as the current source plus the current that flows through the inductor. Alright, so now that I have this equation, I start apply Ohm's law across some of these elements. So for example, I know that because these two elements are in parallel with each other, the voltage is the same. So I can apply Ohm's law over here and say that the voltage across the capacitor divided by 2 is the same as the current through the resistor, and I apply exactly the same thing through the current through the capacitor, which is Vc over the respective impedance, equals to 10 plus I of L. Alright, so I have that equation. Now I can see that Vc is a common factor. I can put it out. And another thing that I can do is to write Vc in terms of V of L. And notice here that Vc, it's simple as the difference between 10S minus VL. And VL is related with IL by applying Ohm's law. So if I plug this equation here on the top of VL and then all these here on Vc, I get this following equation. All right, now I massage that equation and I put things together and I get to this first expression that you have over here. So there are different ways of doing that and achieving kind of different results, or they are the same results but they seem different. So this one over here, if I divide everything by 2, I get to this point, and then if I divide everything by 6, I get to this point. And the reason why I'm emphasizing these is because you guys should try to get the equations all the time in a form where your S square or your maximum, the maximum order degree here, or degree order of your Laplace should be a coefficient of 1. And that's just because when you, later on, when we go and try to do the partial fraction expansions, when you're doing the cover-up algorithm, you can get different results depending on what you, if you don't use this equation here. So try to reduce your equation all the time to S square, to a coefficient of 1. All right, cool. So now let's see and check if that equation is good before we move on. Because if it's not, that means that we made a mistake in our in our analysis of our circuit. So the initial value property tells us that if IL of S is a proper rational function, then I can apply the limit of S going to infinite of S times IL of S, and that is going to give you the initial value, the initial current. So proper rational function means that the degree of the numerator needs to be less than the degree of the denominator. So if I pick up my Laplace equation, I see that I have degree of 1 on the top and degree of 3 on the bottom. So I'm in good shape. It's a rational function. Cool. So the initial value theorem tells me that the initial current is going to be equal to this limit that you have over here. So I'm picking up my IL of S, and notice here that this S is going to cancel out with that S. But if I substitute S by infinite, I don't get anywhere out of these. So one of the tricks that we do in this case is to actually substitute S by S going to infinite by 1 of S tending or going to 0. So all I did was so S cancel out, and then I divide everything by the highest degree, S square, and rewrite that equation that you have over here. Now if I substitute that by zeros, notice that I have 0 divided by 1, 0 amps. And how do I know that this is correct? Well, it complies or agrees with the initial current that we found early on step number 1. All right, so we're not done yet. We need to check the final value and see if the equation is correct. And the final value tells us that all the poles of S times IL of S need to be on the left half of the S plane. All right, so this is my equation. Notice that I'm multiplying my IL of S by S. So the poles of interest are from this part over here, from this quadratic equation here. So if I apply the roots of that, or if I find the roots of that, I find the following poles. If I go to the S plane and I draw the poles, they are on the left, the left half of the S plane. So we're good to go and apply the final value property, or the final value theorem, which states that your final current is going to be equal to the limit of S going to 0 of your S times IL of S. So this is my equation. I'm going to apply the limit with S going to 0, and notice that gives me 5 amps. Let's confirm that with the final condition of our circuit. if I go back to my circuit, again, the inductor is short circuit, the capacitor is an open circuit. I get this circuit here, which gives me 10 volts divided by 2, gives me 5 amps, which is the right answer out of my final value theorem. All right, pretty good. So far our equation seems correct, or it's valid with the initial and final value theorem. Let's go and start doing the partial fraction expansion. So I'm going to rewrite my equation now with the poles on the denominator. I don't need to write the zeros, they can just be like this. And the goal is to separate the poles from each other with the respective k1. And this is what's called partial fraction expansion. And now I need to find those k's. Alright, to find those k's, we're going to apply that cover-up algorithm that tells you that for your k of interest, you do that respective pole times your equation, and you find the answer for that pole. You substitute on the s's by the pole of interest. Here I want to emphasize two things. We have now two equations. So we have this first one where the roots are not on the denominator, and then we rewrote so we can have the roots on the denominator. And whenever you have your case, or whenever you're trying to find the case for real poles, you're going to use this equation. And whenever you want to find the case for complex poles, I recommend to use this equation. Alright, so let's focus on K1. K1, this is a real pole, so I'm going to use this equation. And all I do is multiply by my IL of S by S, which cancels out this S over here. And I just need to find now the answer when S is equal to 0. And I get number 5. For K2, it's a complex pole, so I'm going to use now IL of S in a complex form here. And I'm going to, so notice here, if I substitute these by this pole, which is the pole of interest, it's going to cancel out, and I just get the S, and with a pole with a positive imaginary part. And I substitute now in all this equation by this, and I get a 2.82 and an angle of minus 151.65 degrees. All right, so I'm going to now rewrite my IL of S with the respective answers. So I'm just substituting the case by the values that I found before. And this is now in a good form to start applying the inverse Laplace, which makes our life easier. So let's see how is that done. So I start with the first one here. It's simple, a step. So I get a 5 times the step. And over here I apply the respective equation for complex number, which gives you 2 times the magnitude of my K2 times exponential of your minus alpha, so this part of the complex number, times cosine and then beta, which is this part, plus your angle, which is minus 151.65 degrees. All right, so I put all together, which just puts as a common factor the step function. All right, I have my inverse Laplace, and how do I know now that that response in time is correct? We should validate our answer. So I'm going to plot. I'm going to use Desmos, and just pay attention here that Desmos wants radians, so I converted the angle to radians. So just let's see how is that done in Desmos. All right, so I extract the graph from Desmos, and I pick some points here, some reference points, so we can have some data and understand if it's correct. I can see that my initial value theorem is close to 0 amps. That's good. And my final value theorem is equal to 5 amps. I have here a peak of 7.5 amps, and then dips down to 4.1, and then 5.3, and eventually follows the final value. And what else can we do? We can actually simulate. Let's do the simulation now using multisim. Alright, so simulation from multisim gives me this answer. I also selected a point over there, maximum point 7.5 amps, which is similar to what we plot on Desmos. My initial value theorem is also 0 amps, and my final is 5. And I have like similar peaks, points here, so 4.1 and probably 5.3, something like that. You can use other simulators. You can use, for example, every circuit or Falstad. Just a heads up that I should have put a ground, the reference point here. By default, I believe it's here, but I highly recommend all the time to have a reference point. But I would say the challenge with these interactive simulators is that the window of simulation is very short, so around probably 1 to 2 seconds on Falstad, and probably like 10-15 seconds on every circuit, which makes it a little bit harder to see the overall answer. Let's just see some of those videos so you can get a grasp. Alright, so you saw every circuit and Falstad simulation, and in summary, if you follow these steps, you can solve pretty much any linear circuit in the Laplace domain. So make sure that you go step by step, and before you move to the next step, make sure that you validate as much as you can your answers.